very good morning to all of you. So, today we are going to start the homogeneous flow theory, the simplest possible analytical flow model which we are going to discuss. We are going to start it today. Okay. So, here what do we assume? We assume that the two phases, they are thoroughly mixed up with one another. They are completely mixed up with one another, so that they can flow as a pseudo fluid. Okay. And what are the basic assumptions of this particular model? Naturally, two fluids are uniformly mixed and they are moving as a pseudo fluid at the mixture velocity. Okay. So, therefore, this shows that both the fluids, this automatically implies that the slip velocity between the two phases, it is negligible, and on other words the two fluids are moving at the same average velocity. So, what does it imply? It implies, the first thing which it implies is, number one, that the two fluids are moving at the same velocity, which is the mixture velocity. In other words, u1 equals to u2 equals to j. Agreed? Okay, this is the first thing that it implies. Automatically the next thing which it implies it, that since there is no slip between the phases, due to the slip alpha was not equal to beta. You remember? So, the next thing which automatically implies is alpha equals to beta, or in other words alpha is nothing but equal to q2 by q1 plus q2. So, what does this imply? This implies that under these circumstances alpha becomes a measurable input parameter. If we know the flow rates of the two phases, which is very easy, the inlet flow rates, you just have two rotameters or any particular flow meter, you can find out the inlet flow rates. Moment you know the inlet flow rates, we can find out alpha. So, now under such circumstances we find, I will just put the heading here, although you know what I am teaching. So, you see that we have come for a very drastic simplification under this particular case, and what has this given us? This has given us that the inlet void fraction and the in situ void fraction has become equal, or in other words the void fraction or the in situ composition is nothing but a measurable parameter. So, therefore, in this particular case, just remember, just for recapitulation, suppose there is evaporation, condensation or boiling, then in that case we can obtain the quality from the mass fraction, the inlet mass fraction, and the void fraction from the inlet volumetric flow rate. And finally, the third assumption, this is simply attainment of thermodynamic equilibrium between the phases. This has to happen. Unless there is any thermodynamic equilibrium between the phases, there will be heat transfer, momentum transfer, there will be energy transfer, there will be mass transfer. Moment those things happen, then there obviously under such circumstances we cannot have the homogeneous flow assumption, okay, because the entire thing has to be uniform throughout. So, therefore, the three assumptions, remember, mathematically if we express them, it is just that u1 equals to u2, which is equal to either UTP or J. J is a better thing, we can relate it with volumetric flux, so we call it J. Other thing is alpha equals to beta, and then attainment of thermodynamic equilibrium. These are the basic and very drastic assumptions which govern the homogeneous flow theory. So, under what circumstances are they applicable? Naturally, they are applicable for bubbly flow situations. Okay, it is not exactly bubbly, I should say dispersed bubbly, where the bubbles, they are dispersed uniformly. If you remember when I had drawn the pictures, this should be corrected as dispersed bubbly. That means the entire thing in the entire thing, it's sort of this particular appearance. This particular appearance, this is the correct thing. Moment the bubbles become larger and they get deformed, the non-uniformity goes away. Under this particular condition also the homogeneous flow model does not apply, but we apply it, see how much deviation is there, and then we suggest some suitable correction factors. Okay. So, therefore, the ways of application are firstly the bubbly flow, droplet flow, mist flow, it is the same thing or almost. Wispy annular, when the film is very thin, but wispy annular is not a very correct thing. Actually, in wispy annular what you should be doing is, it is a very interesting situation actually. We have a liquid core, we have gas, and then here we have big chunks of liquid. As a matter of fact, I will tell you that bubbly and wispy annular, they are not very different, other than the fact that in bubbly the entire thing looks like this, in wispy annular a very thin liquid film can be observed at the walls. It is very difficult to differentiate between the two under ordinary laboratory conditions. I will be requesting Amit to show them bubbly and wispy annular and just tell them how difficult it is to differentiate between the two. So, under such circumstances, more or less we can use the homogeneous flow assumption. Now, let us see under which circumstances we cannot use it at all, even if the two phases they are completely mixed with one another. I agree, but it is flowing, maybe it is flowing through a orifice or a very short nozzle. Under that circumstance, what do you expect is going to happen? Completely mixed flow, but it is flowing maybe through a very short nozzle or maybe through an orifice. Orifice means an abrupt contraction. Then what is going to happen? Rapid acceleration will take place. Under this rapid acceleration, then we cannot have the two phase flow situation. This I have already written down here. Okay. So, this is one thing where we cannot have, and for the rapid acceleration, what is the problem? Let the two phases accelerate. Why cannot we use it? Because under such circumstances there is a drastic reduction or drastic change in pressure. Moment there is a drastic change in pressure, flashing occurs. Moment flashing occurs, thermodynamic equilibrium is no longer valid. Clear to all of you? So, therefore, whenever we encounter any particular situation where there is a flow through a short nozzle or maybe through an orifice where there is a rapid acceleration, flow through rapid change in area, under such circumstances, since the equilibrium condition is not valid, we do not have your homogeneous flow theory. Okay. So, therefore, certain specific cases I would like to read out: flashing of steam water mixture through short nozzles and orifices. We cannot use the homogeneous flow theory. Next, say bubbling in superheated liquid. Why? Because in this case we have to consider bubble nucleation, bubble growth and things like this. Then supercooled vapor, that also condensing in high velocity stream. So, these are the things, if you can note down, you can note down the situations where this is inapplicable due to rapid acceleration and pressure changes. I have just mentioned this, but I have not given the specific examples. Flashing of steam water mixture through short nozzles and orifices, bubbling in superheated liquid, or supercooled vapor condensing in high velocity steam. Okay. Suppose we have non-adiabatic flows with changes in quality. All these things, moment all these rapid changes in quality etc., rapid change in pressure etc. takes place, thermodynamic equilibrium, the last assumption which I had shown in the previous slide, if you remember, this assumption is no longer valid. Okay. There is another very interesting situation where we cannot use homogeneous flow theory. That is, suppose you have countercurrent flows. Okay. Even if it is a bubbly flow situation, you have countercurrent flows, then in that case the flow is driven by gravity or vertical flows, and in this case the gravity, it acts on the different densities of the two phases. Moment gravity acts on the different density of the two phases, in this particular case can you define a suitable average velocity? Do you understand? Because in this particular case, say u minus u1. So, here a suitable average, or in other words, can you tell that u1 equals to u2 equal to j? Definitely you cannot say. So, even if it is maybe a mixed sort of an appearance also, for counter current flows we cannot use the homogeneous flow assumption. Remember these things. So, these two circumstances just remember, whenever there is rapid changes in say area, pressure, etc., non-adiabatic flow situations and for counter current flows. These are some of the limitations. Okay. So, now let us go into the basic derivations. Do not look into the slide, we are going to derive it, but I have put down everything in the slide just for your convenience, so that we can you can refer to it. Okay. But for the time being we will not be looking through the slide, we will be deriving them ourselves, and we will see how the derivations are different from what we have derived for the single phase flow equations. So, let us start with the say continuity equation. For single phase flow, what is the continuity equation? It is nothing but the conservation of mass. So, the total mass is W, that is equal to rho u A. This is for single phase. Here what should I write? Here same thing, the total mass flow rate has to be constant, is not it? So, therefore, we can write down the individual mass phases might vary, but the total one has to be constant. So, therefore, this has to be equal to rho Tp, okay, u Tp, or you can write it down as J into A. We can write it in this particular way, okay, where we know that rho Tp it is nothing but equal to, as I have already mentioned, and this u Tp is nothing but equal to Q by A. So, therefore, we find all of these are measurable parameters. Okay. Fine. Next, if you go to the momentum equation. Momentum equation, if you remember in the last class also just we had derived it. What was the expression for single phase flows? It was minus dP dz, it was equal to S by A tau wall shear stress. This was the derivation for single phase flows. Now, for two phase, homogeneous flow, what should I write it down? Pressure gradient. This will be equal to wetted perimeter by cross sectional area, that is the pipe, so no problem. This has to be two phase, agreed. Now, we cannot say tau w is equal to tau w two phase. Why we cannot say? Because tau w two phase, that is a or rather any wall shear stress, it is a function of friction factor. If it is a function of friction factor, it is a function of Reynolds number. If it is a function of Reynolds number, then try to understand or try to remember, for only liquid flow, what is Reynolds number? It is dG by mu L, or in other words d u L rho L by mu L. For two phase flow, then naturally what happens, the frictional pressure gradient dP dz, say frictional for single phase flow, this is nothing but a function of your friction factor single phase, okay, which is a function of Reynolds number, say single phase, right. Now, for two phase flow situations, just remember two phase, this will be a function of friction factor two phase, which is a function of Reynolds number two phase, agreed. Now, definitely this Reynolds number two phase and Reynolds number single phase, they both of them, firstly I really do not know how to define two phase flow Reynolds number, okay. But even if we define it also, then it should be this one is equal to dG by mu L. In this particular case, d is fine, diameter of the pipe, GTP is also fine, the total flow rate, but this definitely has to be mu Tp, isn't it? Where mu Tp, it will be a function of composition and things like that. So, definitely mu Tp can never be equal to mu 1 or mu L, whatever it is. So, therefore, we find out that even if we assume homogeneous flow theory, but then also your frictional pressure gradient for the two cases will not be the same. Agreed? So, therefore, to continue with this, here we have instead of S by A tau W, we have tau W two phase. Then here it has to be rho Tp g sin theta, isn't it, plus GTP dUTP dz. Agreed? Where this is the frictional pressure gradient, this is the gravitational pressure gradient, this is the acceleration pressure gradient. Okay. Similarly, if we take up, we will just do the three equations and then we will expand the momentum equation to find out how to find out the pressure drop or the pressure gradient from known input parameters. So, energy balance equation, if we take up, same thing that we had done in that particular case, it was d cube was equal to dH plus d half u square. Just in the previous class we had defined it. This particular case also it is going to be d cube. Suppose this was for unit mass of single phase flow. For two phase flow, what do we get? Two phase flow, this is going to be dq equals to, if it is not for unit mass, then we will put a WTP, DHTP, sorry ddz of DHTP plus UTP square by 2 plus g sin theta into z. This is the energy balance equation that we can write. Okay. If we are having some sort of a heat transfer, maybe some sort of condensation evaporation, then probably we will have to use the energy balance equation. Okay. Now, if we consider these equations, what do we find? The momentum equation and the continuity equation. The momentum equation I have already shown, okay. And in the continuity equation, so we find what are the things that we are supposed to determine. Rho Tp, which we can find it out, UTP, that also it is an input parameter. If we take up the momentum equation, well, let me write it down once more. Some sort of overwriting has taken place there. So, therefore, this is going to be, this is equal to say minus dP dz frictional, or I will put it as in this particular way itself. This is the expression which we had obtained. Now, in this particular scene already I have told you how to define rho Tp. This I have told you how to define. So, SA etc. you already know. So, therefore, as I have told you that let us take up term by term and see how it can be expressed in terms of measurable parameters. So, initially let us take up the frictional pressure gradient. Okay. So, this minus dP dz f two phase, naturally it is for the two phase flow situation. How can we, suppose we take the analogy from single phase flow equations, then we know that this frictional pressure gradient can be expressed in terms of friction factor and other things. What was the basic definition? I do not know whether you remember it or not. This is frictional factor rho Tp UTP square. This equation definitely you should be remembering, is not it? So, or in other words, this can be written down as 2 Tp FTP say g square by rho. Can we write it down in this particular term? we are replacing this with g square by rho Tp. Okay. Now, as I had already mentioned previously, this 1 by rho Tp, this can also be written down as 2 by d f Tp g square, agreed, and this particular term, this can be defined in terms of quality. Okay. So, this can be expressed in this particular form, agreed. Okay. And again x, as I have already mentioned, this is nothing but we can, this is also a input parameter, fine. So, therefore, if you substitute this, then from there what do we get? We get the frictional pressure gradient for the two phase flow situation. This is obtained as 2 by d f Tp g square, and this particular term, this can be written down as V1 plus x V12. Why I have written it in this particular form? Because if we have to find out the properties using your Mollier charts, steam tables, etc., then from there it is very easy to get V1, V12 and so on and so forth. So, therefore, this can be written down in this particular form, agreed. Then if we take up the, we find that here everything we know except this FTP term, this is the only unknown, other than that all the terms we already know, isn't it? Acha, there is one other form by which also we can derive it, that also I can do it. This is, before I do this, I had started it with, sorry, rho Tp UTP square. Okay, the basic, if you see from where I had started it. Okay. So, this then I had substituted it in terms of g square by rho. Okay. Instead of that, we can also write this term as rho Tp into UTP equal to g, GTP or g. So, we can write it down as g square into j, right, UTP equals to j, I have already said. Whatever way you wish, you can write it down, it is just depending on the availability of the data in which form you would like to express. So, we can either take up this particular form or we can take up this particular form. Okay. Whatever form you take, you find all the terms you know except the equivalent friction factor, fine. So, this was all I had to say about the frictional pressure gradient. Let us take up the gravitational pressure gradient. How did we express the gravitational pressure gradient? It is simply the mixture density. Okay. So, this you can write it down as Q2 by Q, or whatever form if you want, you can write it down and you can express it. Okay. Even you can write it down as beta rho 2 plus 1 minus, whatever you wish. This is something not very important, this can be done in a straightforward manner. Okay. Now, let us take up the acceleration pressure gradient. Acceleration, please remember these terms, the final expressions which we have obtained for the frictional pressure gradient, the gravitational pressure gradient. Okay. Suppose we take up the acceleration pressure gradient. How did we define it? G du dz, agreed. Okay. Now, why does acceleration take place in this particular case, can you tell me? If there is no heat transfer, nothing, okay, under adiabatic flow condition, can you tell me why this acceleration pressure gradient happens? This happens, see, a flow is occurring. Why is flow occurring? There must be a pressure gradient. If the pressure gradient is under normal circumstances we find that the pressure drop or the pressure gradient is not so very drastic that it will affect the specific volumes of the two phases. But if the pressure drop is very drastic, then naturally what is going to happen? Your the density of the fluids are going to change, particularly the compressible fluid, isn't it? Maybe it is a air water flow, the water density will not change, but the air density is going to change, isn't it? So, remember one thing, particularly if one of the phases is a gas phase, then we can have acceleration pressure gradient. How important or how high it is going to be, that will depend on the circumstances. Under normal circumstances, maybe the pressure drop is not so very high that it is going to affect the density of the gas phase. Okay, but there will be an acceleration pressure gradient whenever there is a two phase flow, particularly when one of the phases is a gaseous phase. This particular thing we do not say for single phase liquid flow. Agreed? So, therefore, this particular this acceleration pressure gradient, this arises just because one of the phases is compressible, or in other words considering the compressibility of the phases. And there is one more thing, if there is an area change. So, therefore, this UTP, in order to evaluate dUTP dz, what we have to do? We have to express it in terms of those particular quantities which will be affected due to with axial distance, or which will contribute to your acceleration pressure drop. So, how can we express it? We can write it down as d dz of, again basic definition. Can we do this? Agreed? This particular term, this is constant. The things which will be affected with distance, just because pressure changes with distance, is this term and this term, isn't it? So, therefore, we can write this down as can we do this? Okay. Now you perform these particular integrations, these particular differentiations, and what do you get? You get GTP, WTP, and if you perform these particular differentiations, then in that case what you get is by rho Tp d dz of 1 by A, okay, plus d dz of 1 by plus GTP WTP by A d dz of 1 by rho Tp. We can write it in this particular form. Agreed? Now, if we do this from here, what do we get? d dz of 1 by A is nothing but minus 1 by A square dA dz, right. Okay. So, this we can substitute in place of this, and if we have to do this, how can we write down 1 by rho Tp? 1 is, this is nothing but equal to Vtp. So, this can be written down as x V2 plus 1 minus x V1, yes or no? So, we can substitute them and then we can get an actual expression of acceleration pressure gradient. Do it and then let us see what you are going to get. So, from this particular situation, the thing which we get is it is specifically equal to, if you do it and to find it out, this is specifically equal to minus g square Tp by rho Tpa dA dz, isn't it? One of the A's has been taken up here, one of the A's has been taken up with WTP to give you a d square, and one of the A's are remaining. Okay? And the other term, if you do it, then the thing which you are going to get is g square T p V 2 minus V 1 dx dz plus x dV 2 dz plus 1 minus x dV 1 dz. Just see whether you are getting all these 4 terms or not, 4 rather 5 terms, okay? Because the thing is, here if you write it in this particular form, both x might vary as well as V 2 might vary. X varies only when there is a heat transfer, and V 2 varies when there is an abrupt or rather a very rapid increase in pressure. So, to keep matters normal, we will be considering all possible things that can happen. Okay. So, therefore, from here if you differentiate, we get dx dz V 2 or V 2 dx dz plus V 1 minus V 1 dx dz, agreed, and then we get V 2 dx x dV 2 dz and 1 minus x dV 1 dz, is not it. So, I have combined all of them and I get this is the total expression. Now, in this expression you see why is this particular V 1 varying with z? It is varying just because it will vary only if V 1 is a function of pressure. So, therefore, if that is so, then this can be written as dV 1 dP dP dz, yes or no? Usually this term is negligible because 1 is taken as the liquid phase, and similarly this term it can be written down as we can write it down in this particular form, agreed. So, therefore, you substitute in this particular total expression of dP dz which we had obtained. In this particular total expression, you substitute the frictional pressure gradient from the expression which we had derived. Frictional pressure gradient can be substituted from this particular expression, then the acceleration pressure gradient it can be substituted from this particular expression, and the the gravitational pressure gradient can be substituted, and the acceleration pressure gradient that can be substituted from this particular expression. We find that we get the acceleration pressure gradient only when there is a rapid change in pressure due to which the specific volumes change, or if we have a change in area. Okay. So, if you substitute all of these in the total expression of minus dP dz, just substitute them and then tell me what is the final expression that you are getting. Substitute them. Let us see what is the final expression that you will be getting. Final expression that we will be getting is minus dP dz. This will be equal to 2 by d FTP V1 plus x V12 plus, let me keep it as rho Tp because it is an input parameter. Acha, sorry, the z will not be there, very sorry. This I had written it earlier also because this is the pressure gradient. Where did none of you pointed out this mistake to me? Where did I make that mistake? Initially also, probably I cannot find it now, but anyhow z will not be there. I did not mention it, okay, fine. So, this plus this is the other term due to area change, then we have those particular terms due to quality change and due to so, this is the total expression for the pressure gradient. Now, let us take all the pressure gradient expressions to the left hand side. Under that circumstance, what do we get? We get an expression as this is the expression and this divided by, because everything has been taken to the left hand side. So, this divided by g square 2 phase this is the final expression that we get for calculating the pressure gradient when two phase flow is occurring under homogeneous flow condition. The entire thing has been written down in this particular slide and this is the final expression which we have derived. Now, if you observe this particular expression, what do you get? You find out that more or less all the terms are input parameters except FTP. Okay. So, therefore, the next thing which we would like to do is to discuss methods by which we can express the two phase frictional pressure gradient in terms of certain input parameters or in terms of whatever we know in terms of or in for the case of single phase flow. So, we cannot idealize one particular definite unique method of defining FTP, we will be discussing the different methods. And other than FTP, if you observe both the numerator and the denominator, you find that other terms which we have, the pipe diameter, the mass flux, even the quality change with length, this can be obtained from enthalpy balance if at all there is a heat balance, otherwise this term cancels off. And the other thing, the phase physical properties, the taper, if there is a taper then we have this term, otherwise this term also cancels out. So, therefore, more or less everything else is a, we can obtain everything else from known input parameters. Okay. This we have done for this situation, we have considered there is an area change. Any doubts you want to ask? The cos theta is written there, that probably we have taken it with respect to the vertical, but it should have been sin theta because every time I consider from the horizontal. Very true, that is very true. This is not very correct, in my slide I have written it down as sin theta there. Okay. Now, remember one thing, under what circumstance have I derived this? I have derived that, well, there is a taper due to which there is a dA dz. Okay. And I have assumed that there is a frictional pressure gradient, there is a gravitational pressure gradient and there is a quality change due to heat input or output. Okay. So, therefore, please remember in this particular equation that I have shown, your dx dz, this x I have assumed this varies only with z and this variation occurs due to heat transfer. Tell me one thing, if I have significant flashing, say, okay, there is a heat input also and there is significant flashing with it. So, therefore, then what happens? If there is significant flashing as well, then in that case along with pressure your x should also change, isn't it? So, therefore, under that circumstance for this particular expression what have I assumed? I have assumed x is a function of enthalpy only. So, if I know the enthalpy balance I can find it out. For significant flashing, if there is significant flashing, that condition will x be a function of enthalpy only? Under that condition it will be a function of both enthalpy as well as pressure, right. So, therefore, under that circumstance then in that case your dx dz that cannot be obtained from enthalpy balance alone. You agree with me? So, under that circumstance dx dz can be expressed as del x, it has to be expressed in terms of h as well as in terms of p. Okay. So, it will be del x del h at constant p dh dz plus del x del p at constant h dp dz. You agree with me? So, therefore, if that is there, then instead of the dx dz that I have mentioned here, this has to be replaced by this whole term. Do you agree with me? And then what is this term, can you tell me? What is this particular term? Any idea? At constant pressure, how enthalpy changes with quality? Latent heat of vaporization. So, therefore, this is nothing but H12, in other words this is nothing but equal to 1 by H12. You agree with me? So, therefore, for that circumstance we can write down dx dz, it is nothing but 1 by H12 dh dz plus del x del p at constant h dp dz. Can we do this, yes or no? So, therefore, this is the acceleration pressure gradient in presence of flashing. So, for that what happens, if there is a taper, there is an area change. If there is rapid pressure changes, the specific volume of either both or either of the fluids might change, and then if there is significant flashing, then enthalpy will also change with, sorry, not enthalpy, your quality will also change with pressure. So, instead of the dx dz which I had shown you, instead of this particular dx dz term, we need to substitute it with this particular expression. So, if we do it, then what do we get? If we do it, then you can do it for yourself, you can practice. Please derive all the things that I am doing in your, when you go home, because it is very important that you know these derivations, otherwise it is going to be very difficult, because gradually you find that the expressions are getting larger and larger. So, unless you derive them regularly, it is going to be very difficult for you. Okay. So, we find that if we do it, then finally the expression of pressure gradient, it has the frictional pressure gradient. If you compare the two, it has the acceleration pressure gradient due to area change, it has the gravitational component, and along with this it also has the one particular term which shows how enthalpy changes with dz. And more importantly, if you observe the denominator, you find instead of considering the specific volume changes with pressure, apart from this we are also considering how quality changes with pressure. So, therefore, we find that the expression in this particular case, it becomes much more involved. Okay. So, one thing which has to be discussed here, there are two aspects which I would like to discuss in the derivation which I have made. Firstly, in the derivation we find that other than FTP we know everything. So, next we will be discussing the methods of finding out FTP. And the other thing is the significance of the denominator term which I have obtained. If you observe the denominator, you find that I presume I had derived compressible flow situations for you, isn't it? So, after this class we will be going a little for compressible flows, because I am not very sure how much you know about it. So, for some of you it may be a repetition, small amount of compressible flows I will be deriving, and once, or rather I will be discussing. Once we discuss that, then the denominator which I had obtained while deriving the pressure gradient for compressible flows, that will be clear to you, and from there by drawing analogy we can know how this particular denominator term, how it is important or what does it signify. Okay. So, that the next class I will be discussing some amount of compressible flows, then we will arrive at the significance of the denominator term which we had derived under that circumstances, and then automatically from analogy we can understand how this particular denominator term is important. Okay. But before that, today I would like to start some discussion on the estimation of FTP, because that is the only bottleneck in this particular expression. Now, what can be the different techniques for deriving FTP? Okay. Now, first thing is, suppose it is low quality vapor liquid mixture. Okay. That means vapor is in a very small amount. Under that circumstances, I can write it down here, FTP, it is nothing but equal to F LO we write. What is this LO? This means that it is a friction factor when liquid only flows through the pipe. Since the vapor quality is very less, then in that case we assume that your frictional pressure gradient or the frictional pressure, it arises primarily due to the flow of the liquid phase of the two phase mixture. Okay. So, under that circumstances we can assume that FTP is equal to FLO. LO means when liquid of the mixture is flowing alone in the pipe. So, this FLO what it is? It is a function of RELO, agreed. What is this RELO, can you tell me? This is nothing but D, the mass flux, okay, U rho is a mass flux of the liquid phase only, that means G1, agreed, by mu 1, or in other words this is dG into 1 minus x by mu 1, agreed. Okay. So, if we take that, then from this particular slide you see that the frictional pressure gradient, instead of this particular FTP, we can express it in terms of FLO. Okay. And therefore, under such circumstances your frictional pressure gradient can be predicted from this particular form itself. Okay. So, we can derive it from this particular form. Okay. Now, one thing I would like, this is one particular thing that we can do. If we are having a very high quality vapor liquid mixture, for that situation we can write down FTP equals to F gas only, agreed. So, for high quality and low quality, these can be two circumstances. For most of the cases it is neither a very high quality mixture nor a very low quality mixture, both of them can be in comparable amounts. If that circumstance happens, then in that particular situation usually what we do, we can write it as a function of two phase Reynolds number, where this two phase Reynolds number can be expressed in terms of dGTP by mu Tp. This is a much more realistic expression as compared to your this particular expression and this particular expression. But the problem which arises with the expression, or the problem which arises by expressing FTP as a function of two phase Reynolds number is, moment we have a two phase Reynolds number, then a two phase viscosity has to be defined. So, this two phase viscosity, naturally it has to be a function of the composition of the two phase mixture, is not it? So, what sort of function will it be? It will not be a very straight function, because remember how this viscosity term has emerged. It has emerged due to the shear. Okay. So, it cannot be a very straightforward function just like density. So, therefore, the problem with the third definition, there are three definitions. One is this, this is for low quality vapor liquid flows. Then we can also assume this is equal to this for high quality vapor liquid flows, and the third thing is FTP is a function of Reynolds number, where Reynolds number is dG by mu Tp. These are the three ways by which we can define, and we find that there are problems with this, there are problems with, they are for very idealized situation, and here the problem is to define the mu Tp. Okay. So, in the next class we will be discussing different ways of deriving mu Tp, number 1. Number 2, we will be finding out that for all the cases that we have done, we can express the two phase frictional pressure gradient under homogeneous flow condition in terms of the single phase pressure gradient when either it flows as liquid only or it flows as gas only. This is a very conventional way of doing in two phase flows, and this particular expressing two phase pressure gradient in terms of single phase pressure gradient, they are usually done in terms of two phase multipliers. They are basically the correction terms which have to be incorporated two single phase pressure drop expressions in order to obtain two phase pressure gradient. So, we will be discussing the two phase multipliers and we will be discussing different ways of defining mu Tp and so on and so forth. So, in the next class we will be continuing this particular discussion. Okay. Thank you very much.